Good morning. I'm Bruce Watson. I'm Assistant Director of the CoE. And our speaker this morning is Professor Syamala Krishnannair. She is affiliated to the Department of Mathematical Sciences at the University of Zululand. Her research interests are in process data analytics, process monitoring, fault diagnosis, advanced multi-scale, multivariable statistical methods, in particular used for fault detection in nonlinear dynamical systems. This research is multidisciplinary. It overlaps with the areas of applied maths, applied statistics, and data science. She's published in peer-reviewed journals and conference proceedings, and her work has been funded through a Tutuka grant and capacity development grant from SASL. Professor Syamala will be talking today on process monitoring using singular spectrum analysis and its variant. We welcome our speaker.
Thank you. Thank you, Chair, for the introduction. My title is Process Monitoring Using Singular Spectrum and Different Variants of Singular Spectrum. So here I'm not including all the variants. I'm only focusing on two variants that and the case studies and the corresponding results. So process monitoring, when we talk about the process monitoring, we know that it's very important because the modern industrial operations are like highly automated, and also it's like very, very complex. And then the continuous monitoring is necessary because it can continuously observe the process and also analyze various operations that has got any deviations or anything like, it's always need for especially for an industrial situation, because of these highly complex units that we have, we need to do that on a regular basis. We need to monitor them. And also it ensures that the processes are operating efficiently, and also it's reliable and within that desired target value or target they are looking for. So it's important in one way. It's very important that we need to monitor any process on a continuous basis. Then if you look at more details on the importance of process monitoring, we can highlight some few things like quality. We need to ensure the quality because the product quality is very important. For that, we have to have a continuous monitoring system. And also the cost efficiency. Cost efficiency means reducing your waste and also the consumption of the available resource that we can fully utilize it. And that so in such a way that we can manage the cost effectively. And also downtime is very important because sometimes you hear about these days, especially with the load shedding and everything, we got some kind of shutdowns. And also for the early detection of the anomalies, so it can even prevent that if we can minimize the downtime. And when it comes to safety, that is also one of the most important thing. It prevent any accidents or something that we don't want it in the processes. We heard about, we know about quite a lot of accidents that could prevent if we had a good automated monitoring system, and that can be also avoided if you have a well system in the industry. And also important that for example, for the control engineers who are working at the process, we have to give some insight about the data that they are using. So in that way they can improve the process. So it's a data-driven insights that we can do, especially us, like we are not the control engineers. We are not we are like mathematicians or data scientists. So for us, we can give that insight through this kind of monitoring methods. So these are the some important important aspects of the process monitoring. So when we look at the loop in a process monitoring system, these are the key components that we need to consider when we want to develop a system. So first thing is the data collection. So when you talk about data collection, we've got sensors at the unit, and we based on using the sensors, we can thousands or 10,000s or huge data that we can collect on every second or every minute like that. So it should be available, and then one can do some data cleaning or some kind of thing, whatever, if the data is not sufficient or if there are gaps, you can do that. You can use some statistical methods or something, or machine learning methods for that. Then the second part is the data analysis. So our focus is more on the data analysis part, and the next one and the following one. So data analysis here, we can implement different statistical models or machine learning models, where we need to think about how do we decompose the data, how do we extract the features. So once we have that, then we focus on the fault detection techniques. So basically control charts are used for that. So if there are any anomalies or something that is not good in the data, that can be detected through these methods. And then once the fault is detected, it's very important that we have to communicate, we have to diagnose them, we have to find the root cause of it. So that also part of the building the model, not all the time, but it is necessary. So there are techniques on that. And then after the diagnosis, we can talk about the how do we resolve the issue. We can communicate with the control engineers, so we can provide solutions for that. So these are the important steps that we need to take into, we need to consider it when we develop the process monitoring model. So there are basically 3 techniques that is available in the literature. So they are model-based techniques, analytical techniques, and data-driven techniques. But my focus, my research is that focus more on the data-driven methods. Model-based and analytical, I'll just give you some idea on it, but my research is based on the data-driven techniques. So when it comes to analytical based techniques, so the approach is more on developing mathematical or the physics-based models, and that relies more on the equations and the relationship. So normally they use differential equations or first principles models that will give the fundamental understanding of the process. So in other words, you need to have a fundamental basic understanding of the process that you are handling, dealing with in the analytical model. And there are some advantages and there are some challenges. When you look at the advantages, it's okay if you have a well developed process, and the process you know it very well, then it is okay, that kind of a model. And also it can predict certain behaviors in certain scenarios, and also it can give some insight in the behavior and also the interactions between the variables. But there are challenges when we look at there, when it won't account for all the process complexities, because if the process is highly complex and there are a lot of correlations are there, it may have challenges there. And also there are limited adaptability to the complex and with the nonlinear system. So, and also we need to have an accurate parameter estimation when we use the analytical model. So there are challenges. Then the next one is the knowledge-based one. So knowledge-based one, the word itself is that we need to have a domain knowledge, or some kind of an expertise should be there to build that model. And it's also based on well-defined principles. So, and also it can, as I said, there should be an expert system available, to build that kind of a model. So it is suitable for a process with the known rules and systems, and also it incorporates human knowledge and experience, so that way also it is good. And some solutions we can interpret, the solution that it provides is interpretable also. But when we look at the challenges, as I said, with the analytical model, it is also got limited adaptability. It is not adapted to that changing conditions in the process, and it may not capture all the unobservable or unexpected behavior. And also, as I said, there are rules and all kind of things that we require when we build a knowledge-based model. So when we look at this knowledge and analytical model, based models, so the data-driven method has got more advantage because data-driven models are based on the data that is available. And these days, as I said, there are a lot of facilities are available in the system, in the process, where we can collect the data and we can utilize those data. So the approaches are like, we can even use the historical data and the real-time process data to train the model. And once we have the trained model, that assumes everything is happening in a normal situation, then we can test it with the data that has got some faulty information or whatever you have. And it captures patterns, it captures anomalies, and also correlation between the variables. As I said, all statistical models, we can make use of them. And machine learning models and neural networks are there. So it's more good than, it's very good compared to other models. So look at the advantages, like it's effective for complex and non-linear system, and it also adapts to changing process conditions and patterns. If you have unexpected or unobservable issues or patterns or some incidents are happening, it can capture those features. And any hidden relationship, especially in the large data sets that you have, we can use certain models to capture that information. But there are challenges also, because we need, especially when we use the neural network-based models, we need to have a substantial amount of a large number of data for prediction. Sometimes it may not be available, especially to build the model, maybe it may not be available. It entirely depends on in the sampling time they normally do it. So that can be a challenge also. So also, like if the data is, certain methods have got certain characteristics. For example, if you have a very noisy data, certain methods may not perform well. But also everything depends on the data and the process that you have. So not all the models can give you that accurate, output or accurate results, or when you want to detect the fault or diagnose it. So that can be a challenge. It's really a serious challenge. We have to be very careful about the model that we are going to choose. Then, among these all data-driven techniques in process monitoring, multivariate statistical techniques, they gained a lot of attention, especially the techniques with principal component analysis, because that's the basic technique and they take the correlation between the variable and it's a linear model. And also partial least squares are there, but I focus more on the PCA based techniques. So these techniques, multivariate and also classical multidimensional scaling, that can be also considered. So they extract features in a reduced dimension, because if you have a huge data with a lot of variables, it's always advisable to reduce the dimension. So these techniques can reduce the dimension. And it also can employed, it is employed in the literature very widely to detect anomalies and also identify the pattern, and also, just to make sure, it already proved that it can monitor the process effectively and build the model. Then you tested it and you chose the control limits and everything. It proved it. And another thing is these techniques can be applied as a standalone technique, or also it can be integrated with other spectral methods or maybe filtering techniques. Depends on the complexity of the process or the type of the process you have. Can be a linear or a non-linear process. Depend on the process, you can always make changes on these techniques. So as I said, again, all the techniques that we choose is entirely depend on the nature of the data and also the characteristics of the process, and also is the sensitivity that has got the different types of deviation. So this can be, you need to consider this when we choose the technique. So among multivariate statistical process monitoring techniques, I said principal component analysis gained a lot of attention in the literature because it can handle the large sets of data, and also with a linearly correlated variable, so it can handle them very well. And also it's suitable for achieving stability and reducing variability in a multivariate linear process, and it proved that. And we use this in principal component analysis. Principal components are used to extract the linear relationship among the variables. So that's a transformation you do. You can see on this side, this is the loop. This is the process that we follow, procedure that we follow when we use the principal component analysis. This is your PCA space. You have the score space and you have a residual space, and after decomposing, after singular value decomposition, and then you use the control charts. We can use the control charts. That is the chart for the residual space, that is the Q statistics or squared prediction error. And for the score space, the data in the score space, you can use the Hotling T-square charts, and there are control limits also specified on that. Based on that, you can see where the fault, the anomalies that happened. And once you detect the fault using the control chart, you can isolate them by using contribution plot. So that can be the contribution plot. You can based on the T-square contribution plot or Q contribution plots or other contribution plot. These days, biplots are also used to get more insight into the fault diagnosis process. So this is the basic framework that we normally follow. We can follow when we use principal component analysis for the process monitoring. But as I said earlier, it's a linear method, so it has got its own limitations because it's only extract the linear relationship among the variables. When your data is non-linear, so it won't be advisable. You won't get that desired output. And also remember, any data, any chemical process data or any kind of a data, they are multi-scale in nature because events are happening at different time, at different locations with different frequency levels. I will show you in the next slide, especially in a chemical process system. And also these linear techniques like PCA always assume your process operates as stationary and it's also uncorrelated in time. So there is no autocorrelation among the variables taken into account. So there is these are the limitations really. But these days your variables are autocorrelated and it is dynamic in nature. So there are extensions to handle this. The dynamic PCA was developed to account the autocorrelation among the variable, and also the nonlinear PCA using autoencoders and kernel functions. Those kind of techniques are developed to handle the nonlinear data or nonlinear process. And also classical multidimensional scaling, they use the dissimilarity structure to identify the correlation among the variables. So that also an extension of this multivariate statistical process monitoring techniques. And there are other methods that also integrated into these techniques like wavelets and singular spectrum analysis that they use the method to filter the data and prior to the application of the multivariate techniques to detect the fault. So, my focus is more on singular spectrum analysis because that is more adapted to the data and doesn't need more like any kind of prior assumptions or something. Like wavelets has got some limitation. It is not adapted. You have to choose the mother wavelet. You have to decide which wavelet you're going to use. So those kind of issues are there with wavelets, but singular spectrum, it's the literature is more promising, and so that's why I chose my research is more based in singular spectrum and its decomposition techniques and everything. So in this talk, I'll be looking at two variants of SSA, that is classical multidimensional scaling, because I use that in the decomposition of the singular spectrum analysis, because I will go to the method later, then I will explain that. I also used another technique, that is the kernel-based dissimilarity based spectrum analysis, that is KDSSA. So these are the two variants that I'm going to talk about here. So I did mention that the data is multi-scale in nature. If you look at the data here, these are the different, you got different signals that obtained from different kind of, or like, incidents. That is, for example, you have equipment degradation, equipment failure, sensor failure, or oscillatory disturbance, or red noise. Those kind of incidents are happening. So if anything happens, if in a typical, this is what happens. For example, if you have a sensor failure, you will see a sudden change in the signal, or any equipment failure, you can see a sudden, like, spiking up. But any kind of an oscillatory noise, it will very, very like all over. It's more like the frequency is not that high, but it's the time, it takes a longer period. And also equipment degradation, you can see that. So there are different frequency levels you can see the incidents are happening. For a sensor failure, I will say that maybe a short period of time with a very high frequency. Equipment failure can be also that we can notice it immediately. But the disturbance, like a random noise or equipment degradation or oscillatory noises, it won't be that observable. It can't detect easily if you just look at the signal. So you need to have a technique that can separate these different patterns in a proper way, so that only then you can, I will say that only then you can do a proper fault detection. So what is multi-scale process monitoring? So that multi-scale process monitoring, that means it involves observing and analyzing the industrial process at multiple levels or at different frequencies at multiple time scales. So that's the definition of that. So it's this approach. It offers a comprehensive and versatile approach to understand and controlling the complex industrial process, and the literature is proved that. So it gives you more insight into the pattern. More insight in the incidents or something that is happening, and it can improve the process efficiency, and also you can ensure a reliable operation across the various scales. So by having a multi-scale model, you can decide which level you need to monitor, because you have different levels or different scales with different frequencies. So it depends on the process. Sometimes you can extract patterns from the first scales, or maybe the first scales are not more noisy, but if you have the larger scales, like the last few scales, it will be very noisy. So sometimes you can just monitor those scales and see what information you can extract. So how it works is integrate data from different scales to form a comprehensive view of the process, and statistical and analytical techniques are applied to the combined data to identify patterns, anomalies, and correlations. So by observing this process behavior at multiple scales, it becomes possible to detect deviation that might not be apparent in single scale monitoring like PCA. PCA is a single scale monitoring, so you won't be able to detect it if something is happening at different levels. As I said, equipment degradation, oscillatory noise, and sensor failure. So all are different scales. So to detect anomalies that is happening at different levels, you definitely need a multi-scale method. So that can give you, can give you like more insight onto your process behavior. So singular spectrum analysis is the method, one of the methods that we can consider. So PCA, that, it works same as PCA, but there are added procedure on that. So it's divided, because it's derived from a lag trajectory matrix. That means a matrix with the lagged variable. So you choose an embedding dimension. For example, if you have a univariate data like this, you fix your window embedding length. That can be based on your autocorrelation of the variable, autocorrelation function you can use, or you can use some other methods. So I use mostly like autocorrelation of the variables. So based on that, you choose your lag. So if you choose a lag of 3, and this is the way that you can create your lag trajectory matrix. So this lag trajectory matrices that capture the process dynamics better than any other techniques. And also it consider it, it can take into account the auto and cross correlation of the variables, especially in dynamic PCA. Also you do that. So that's why it's very, very important to have your lag trajectory metrics based on a certain lag, a time window on that. Then you perform the PCA on that. That PCA procedure is singular value decomposition, all other things that you do. You have reconstruct the component, but I'll discuss that later. And singular spectrum, its applications are like information compression, and also it applied in certain areas where they want to reduce the noise reduction, and also the nonlinear identification of the nonlinear components, especially in the nonlinear process. Singular spectrum that is used, especially it is used a lot in the climatology in that area. It's originated from the climatology, and then from there it went to other domains, and then very recently is in chemical process monitoring. So this is the basic methodology of the singular spectrum analysis. So you have a time series, and then you create your lag trajectory metrics based on your embedding dimension. You use different criteria to choose your dimension. Once you have the lag trajectory metrics, you have the covariance metric, and then you use the singular value decomposition. You decompose the series. So where you get your eigenvalues, eigenvector, and all other things. So once you have that, you perform the grouping. Your grouping is performed based on the principal components that you want to choose. So normally there are criteria like percentage variance. Maybe we can say the first principal component that can contribute most of the variance compared to the last few components. So you can do your grouping with your principal components and the eigenvectors. So you need to have that. So once you have your grouping, you perform the diagonal averaging. That is the method. You average through the diagonals that give you the reconstruction of the additive components. So that's what you will get, different components. So you can have very, very noisy components. Also you have other components with less noise, and you have very trend kind of a component, deterministic component. I will say it can separate the signal into deterministic and the noisy one. So depends on the level. If you choose the embedding dimension 3, you should have a 3 different components. If you choose the embedding dimension 38 or 37, you have 38 levels, and then you monitor them accordingly. So this is the basic methodology of the singular spectrum analysis. So here, the signal that you can visualize it like this. This is your original signal. Then if you choose an embedding dimension of 4, your signal will be, there will be 4 levels or 4 scales that you get it, and it will look like that. So you can decide which one you want to monitor. Some of them, in most cases in chemical process monitoring, I got the good results with the first scale where the noise was very less. But with the noisy components, sometimes it gives you a faulty information because of the noise is there, but it entirely depends on the process that you handle. So there are limitations. It said it's a basic SSA. They take the lagged copies of the time series that are analyzed. They are by the linear PCA. So it's a linear relationship. Again, we are looking at. If the data is non-linear, it won't give you that good results because it uses PCA. So as I said, the nonlinear characteristic, with the data with the nonlinear characteristics, sometimes the minor principal components carry always the important information. If you discard them when you do the reconstruction, so you may lose that information. So it's not suitable to use the basic PCA. So in basic PCA also, there was challenges in retaining minor components. And so if you retain them, that has also got some kind of undesirable effect. Maybe you will get like too many levels. You will have if you use the embedding dimension that 38, if I don't discard some, then I will have 38 levels to monitor. So it can be like time consuming, and sometimes it's not it's not advisable to use like a process with a lot of variables, so that it can be a challenge. with the basic PCA. So that's why I tried to develop. There are variants of SSA that use classical multidimensional scaling instead the PCA in decomposition, because classical multidimensional scaling is already like, performed well in multivariate nonlinear process monitoring. Then I use that, and also another version of the the nonlinear version of the classical multidimensional scaling, that is using kernel functions first to transform the data into the future space, and then use the classical multidimensional scaling. So that is called kernel-based dissimilarity, KD, kernel-based dissimilarity, like a multidimensional scaling, or kernel multidimensional scaling, KMDS. So these are the two techniques that I used in the variants of SSA to reconstruct the components. So this is the basic framework of the SSA and its variants. So here you have the multivariate data, and then you choose your, you look at your autocorrelation function. Based on your autocorrelation function, you can choose of each and every variable, you decide your embedding dimension. Once you choose your embedding dimension, that you create the lat trajectory matrices. Then here the decomposition part, where you decide you want to use PCA or you want to use classical multidimensional or KMDS. So this is the variation that I used. I did it. So then the grouping is based on the singular values. You perform the grouping, and after you have different levels. So basically, I didn't discard anything. I just took all the levels, but I kept it one side. When I want to monitor them, I monitor those specific levels only. Then you reconstruct the components based on your grouping that you have. Then you have the different levels so to monitor. So once you have this multi-scale version of your data, or it's a filtered data, it's a noise-free data with different levels, and then you, we can use the multivariate statistical monitoring techniques, that is PCA, like the control charts and also contribution plots to identify or detect the fault, and also to do the fault diagnosis. I didn't do any fault diagnosis here. I only did the fault detection in this study. So this is the basic framework of the process monitoring framework using SSA and its variants. Now, the case study, I use the 10S Esterman process. That is a simulated test problem, and it's they widely used in industrial process control. It got 5 different unit operations, and there are 2 main products they look at by 2 simultaneous gas-liquid exothermic reactions. I'm not that chemistry person, but it's a simulated process, and it monitored. There are 6 altogether. There are 12 manipulated variables, and also 22 continuous process measurements, and there are 90 composition measurements. And out of this 52, I only took 16 variables for the monitoring purpose. And also there were like 21 different faults in the system, but I only took 3 faults. Those 3 faults were like very, very difficult to observe or to detect, because in most of the literature, with the linear techniques and also with these extensions, these three faults in the system couldn't detect it, because it's normally unobservable in the process. So when we use the SSA based techniques and its variants, we could detect those 4 faults, because the fault 3 is normally a step change that happened, that is in the D feed, that is the variation that happens in the temperature. And also there are the fault 9, it was like a random variation that also is a normal normal faulty things that you normally happen, any kind of random variations you can get in any process. And the other one is the sticking. Sometimes when you use catalyst and you do other things in the reaction, you have this sticking issue, especially in the chemical process. So these are the 3 cases that we looked at it. And this in this case, what we achieved with SSA and the dissimilarity-based similar spectrum and kernel-based dissimilarity KMDS, we achieve the reliability. The reliability means, the percentage of the point, the faults that the number of points that exceeded the control limit. So you have a train model and you got a test model. Train model, you assume the process is operating at a normal condition. When you have a testing model, then you have these faulty cases. So the points that exceeded the control limits, based on that, we can calculate the reliability, we can evaluate the process. So these are the figures that we had it with that. So you can see in KDSSA, all of them, 100%, all the fault cases were exceeded the limit. But I had challenges. For example, KDSSA, my challenge was, it's a kernel, we are using kernel function. So it's a dissimilarity matrices that we are using. And the dimension of the data is too big. Sometimes if you are dealing with 1,000 data, like 500 data, I have to even look at the matrices, the size of 500 by 500 or 1,000 by 1,000. And the scales, I had a very huge number of scales. So I mean, there were really challenges. And also choosing a proper kernel function, and also deciding on the Gaussian. I mean, I use the Gaussian kernel. So there are parameters that you need to tune before you apply them. So there were a lot of challenges with the KDSSA. But luckily, in all the cases, the first scale, I had to take only the first scale to monitor it. And I had to reduce it because, as I said, the dimension was very huge. And also same thing with the dissimilarity scale based SSA. Dissimilarity scale based SSA, as I said, we are not using a covariance metric. We are using a dissimilarity metric. So it has got challenges when it comes to the dimension. But luckily, we can reduce them by using principal components. But still, that's a challenges, especially when we have a lot of data and with a lot of variables, we had some problems. And in general, I'm still looking at the way that we can tune the parameter. For example, a system that we can, a automated system that we can choose the embedding dimension without any assumptions or anything, and also the grouping the components to extract more features, or maybe features more efficiently. That also we need to look at it. So these are the 2 things I'm focusing more on that. And in conclusion, so I want to say the variants of SSA performed well and better compared to the basic SSA. And I can say this DSSA and KDSA focused more on the dissimilarity structure of the data. But SSA basic SSA focused on the covariance structure of the data. So it has got its own advantage and it has got its own disadvantage also. So basic SSA and DSSA, I had a large number of scales to monitor, because it's not like always I got the better detection in the first scale or the second scale. But KDSSA, I had the detection always in the first scale. Maybe because we use the kernel function, it's more non-linear. So also, as I said, there is an improved reliability when the signals are non-linear, and also when the signals, when you have a signal with undetectable or maybe unobservable faults, so it performed very well compared to other methods. So these are the advantages on this method. So these are some references, and thank you for listening.
Interesting presentation.
Thanks.
Are there questions from the audience?
Yes, I want to ask some question.
Yes, Montaz, please proceed.
Yeah, so Syamala, can you go back where one of the slide you put limitation, and before that there is picture, some graph
Okay,
in the slide.
Okay, let me share it again, Prof.
These are is a measured from this, or is a main one, and you have a wavelet various level, or you have a different sort of measurement for each pixel?
No, Prof, this is the original signal, and that was decomposed into different levels using SSA. So this is the end result.
Oh, okay.
So
well,
the first one is the component 1, then component 2,
okay,
component
yeah.
3, and component 4. So you can see different frequency levels here.
Yeah, so that's the question I have. Then why not using the various level of wavelets and see wavelets as various level and see how that compare with your SSA?
I used it. That was by when I start developing the basic SSA process monitoring technique. I used wavelets, but when you know as I said, the disadvantage was to choose the mother wavelet. So there was always I had to choose WGs or HAR wavelet and to see where I get a good decomposition. And also I have to make the signal in dyadic in length. That is not always possible. Sometimes you don't have that. When you monitor a real-time process, your length of the signal, it won't be always it is available, or you won't get the desired result when you have a 256 or 64.
But I think so HAR wavelet will not be good one. There's some other wavelet that can be.
I didn't, but it will. These days, spectral techniques like wavelets and empirical mode decomposition on all the variations or extensions of that will give you, because basically you are doing a filtering, and you want to reduce the noise, and you want to extract more features, more trend. So it has, each and every technique has got its own advantage and disadvantage, Prof. But I found SSA is more adapted to the data. And
all right, thank you. Thank you.
Thank you, Montaz, and thank you, Syamala. Are there further questions from the audience? Further questions? Then I would like to thank our speaker again. And thank you for joining us, both the speaker and the audience, at the CoE weekly seminar. I presume we will see you all next Friday. Same time, same place. Thank you very much.
Thank you.